Welcome back to this lecture of sequence and series. We shall start with a quick recap of our development so far. In the previous lectures, we introduced the notion of sequence. Informally, by a sequence, we mean an ordered list of numbers. To be more formal, a sequence is defined as a function f from S to R, where S is a subset of the set of non-negative integers. We saw the notation used for a sequence. A sequence can be denoted using the notation n is equal to 1 to infinity. N are called terms of the sequence, and nth term an can be viewed as output of the function f evaluated at n. That is, an is actually f evaluated at n, where f is the underlying function associated with the sequence n is equal to 1 to infinity. Other possible notation for sequence is or we can list a sequence as follows. It is advisable to describe the nth term of the sequence, namely an. I should also remark that though we have written n is equal to 1 to infinity as in the formal definition of the sequence, n may vary from 0 to infinity, or it may vary over some subset of the set n union 0. That is, a sequence may start, for instance, from A4 onwards. We also saw that a sequence can be described in two ways. One is called closed form expression, where sequence an is described by giving a formula for nth term an. For instance, an is equal to 1 by n square for every n greater than or equal to n. Another way of describing a sequence is recurrence relation, or using a recursive formula where instead of writing the nth term an in terms of n, we write nth term in terms of some of its previous terms. We saw a famous example, namely Fibonacci sequence. Though we use the notation an, n is equal to 1 to infinity for a sequence, the distinction between a sequence and a set deserves to be stressed. Note that in a set, order of elements is not important, whereas in a sequence, order matters a lot. Secondly, in a set, repetition of the elements are usually avoided, whereas in a sequence, the elements can repeat. We have given plenty of examples to illustrate all these things. However, keep in mind that a sequence is distinct from a set. Lastly, though not rigorously, we introduce the concept of convergence. In convergence, we investigate the behavior of a sequence as term progresses. In other words, we observe what happens to the terms of the sequence as n becomes larger and larger. Recall that by the notation limit n tending to infinity an equal to L, what we mean is that the terms of the sequence, namely an's, approaches closer and closer to the fixed value L as n becomes large enough. For instance, we have seen that in the sequence 1 by n square, n is equal to 1 to infinity. To be explicit, 1, 1 by 4, 1 by 9, 1 by 16, etc., 1 by n square, etc., we can see that as we progress towards the tail end of the sequence, the terms are becoming close to 0. Hence, we write limit n tending to infinity 1 by n square is equal to 0. We call sequence 1 by n square to be convergent, and 0 is called as the limit of the sequence 1 by n square. Whereas for some other sequences like say minus 1 power n, n is equal to 2 to infinity. Let us say, to be explicit, 1, minus 1, 1, minus 1, and so on. We cannot find a number L so that as we progress towards the end of the sequence, the terms of the sequence become close to this number L. Such a number L does not exist. Similar is the case with sequence like n square, n is equal to 1 to infinity. Such sequences are said to be divergent. Keeping these ideas in mind, let us proceed. I would like to recall the remark I made at the very beginning of the previous lectures, namely the following. In day-to-day life, the terms sequence and series can be used interchangeably. Both are used to denote succession of events or objects. However, in mathematics, these two terms have distinct meaning, and we saw that sequence is used for an ordered list of numbers. Let us proceed to see what a series means for a mathematician. Crux of this lecture will be defining a series. If you recall, finding sum of finite number of real numbers is widely used in mathematics. In fact, in day-to-day life, ranging from a grocery shop, for instance, to a laboratory where sophisticated experiments are being conducted. Let us recall that while finding sum of finitely many real values, say for instance A1, A2, A3, they are real numbers, and we would like to find A1 plus A2 plus A3. Note that the order in which we add these terms A1, A2 and A3 does not matter. That is to say, A1 plus A2 plus A3 is same as A2 plus A1 plus A3, which is same as A3 plus A2 plus A1 and so on. If you recall permutation and combination, there are 3 factorial ways in which we can find sum of 3 real numbers. 6 different orderings are possible. However, all these orderings ultimately result in same sum. To find sum of finite number of real numbers, we can first find sum of 2 real numbers, and to this sum we can add a third real number, see what comes out at the end. Summing up, in the process of finding sum of finitely many real values, the order in which the terms appear doesn't matter, at least mathematically. Of course, when dealing with certain figures, we may observe that certain order is more convenient to work with than certain other orders. For instance, if we are asked to find sum of say 247, 198 and 2, as we observed previously, we can add them in 6 different orders. However, 198 plus 2 equal to 200, which added up to 247 to yield 447 gives the most convenient order. So, we can always resort to such shortcuts to find sum of finite number of real numbers. Now, consider the question of finding sum of infinitely many real numbers. To illustrate, let me give you an example. Let us recall decimal expansion of a real number. For instance, when we say decimal expansion of 10 by 3 is 3.333 etc., non-terminating recurring decimal expansion, what do we mean really? We mean to say that 3 plus 3 by 10 plus 3 by 10 square plus 3 by 10 cube plus etc. is equal to 10 by 3. This is what we mean. Knowingly or unknowingly, in decimal expansion, we deal with sum of infinite number of real numbers. And a natural question here is the following. If we increase number of summons, that is, instead of dealing with 3 plus 3 by 10, if we deal with 3 plus 3 by 10 plus 3 by 10 square, instead of dealing with 3 plus 3 by 10 plus 3 by 10 square, suppose we deal with 3 plus 3 by 10 plus 3 by 10 square plus 3 by 10 cube, 4 terms, and so on. Does it give better and better approximation for the number 10 by 3? Note that to get exactly 10 by 3, we have to keep on adding 3 with 3 by 10 with 3 by 10 square and so on. In fact, we have to deal with infinitely many real numbers. This quest of seeking better approximation, in fact, leads to the concept of sum of infinitely many real numbers. However, let us remark that there are some issues or trouble when we deal with sum of infinitely many real numbers. What are these issues? In what follows, I would like to illustrate these troubles with the help of some examples. First of all, note that while dealing with the question of finding sum of infinitely many real numbers, we cannot keep on adding to see what comes out, because there are infinite number of real numbers. When we deal with finite number of real numbers, say a1, a2, a3, etc., an, and when we want to find its sum, first we can find a1 plus a2, for instance. To this sum we can add, say, a3 and so on. This process will terminate. Whereas, while dealing with sum of infinitely many real numbers, we cannot keep on adding and see what comes out. That's one thing we should keep in mind with regard to question of finding sum of infinitely many real numbers. Now, let us deal with some specific example to see what are all the other issues. Suppose we want to find this infinite sum 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 plus etc. I hope you can guess what's the pattern followed by the terms here. In fact, the nth summand here would be 1 by 2 power n. In this sum, the first number is 1 by 2, second number is 1 by 2 square, third is 1 by 2 cube, and so on. Let us see whether we can find this infinite sum. As I remarked, you cannot first find the sum of 1 by 2 and 1 by 4, then add to this sum 1 by 8 and so on, because it is an infinite process. But then let us view this problem slightly differently with the help of geometry. You consider a unit square whose side lengths are 1. We all know that its area is 1 square units. Let us halve this square. Then area of the first half will be half square units. Let us again halve the second half. The area here will be 1 by 4. Let us continue this halving process. Area of this figure will be 1 by 8 and so on. We can see that the areas of the smaller figures fill the area of unit square we started with. Thus, geometrically, we can observe that the sum of the areas, namely 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 plus etc. amounts to the total area of unit square we started with, namely 1. Thus, we observe that 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 plus etc., the sum of infinite number of real numbers is equal to 1. Let us proceed with another example where we are interested to find this infinite sum. One plus 2 plus 3 plus 4 plus etc. It's very clear that as and when we add more and more term, the result increases. That is, 1 plus 2 is 3, When we add the 3 with this sum, we will get 6. When we add 4 with the previous sum, namely 6, we get 10, and so on. As we add more and more terms, the sum increases. We can see that by taking more and more terms, the sum can be made larger than any pre-chosen value. So, intuitively, we observe that the sum 1 plus 2 plus 3 plus 4 plus etc. cannot be a finite value. This is in contrast to the previous example where sum of infinitely many real values yielded a finite number, namely 1. Thus, when dealing with sum of infinite number of real numbers, we cannot always assert that ultimately this sum comes out to be a finite value. In some cases it may, in some cases it may not. Even to judge whether sum of infinitely many real values will be finite or infinite is difficult. For instance, if we are concerned with this sum 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus etc., it's not very clear whether ultimately this infinite sum amounts to a finite value or not. So, what we observe is the following. In contrast to sum of finitely many real values, when dealing with sum of infinitely many real values, whether we can come up with a finite value or not is not very clear. That's one thing or one difference between sum of finite number of real numbers and sum of infinite number of real numbers. We should not jump to the conclusion that sum of infinite number of real numbers will be always infinite. No, we can sometimes have finite value also. So, a natural question is, how do we assign a definite meaning to an infinite sum? How do we see whether an infinite sum comes out to be a finite value or we cannot find it? These are the questions we have. Let me proceed with some more example to see other troubles that we may come across when dealing with sum of infinite number of real numbers. Let us consider this example. As you see, here we are dealing with sum of infinite number of real numbers, which is alternatively positive and negative, 1 minus half, 1 by 3 minus 1 by 4 and so on. Assume for a moment that this infinite sum comes out to be a finite value. With that assumption, let us proceed to find what is that value. Suppose we try to find this infinite sum with a grouping as follows. With this particular grouping, one can observe that each sum in the parenthesis is positive. So, intuitively we feel that the given infinite sum amounts to a positive value. On the other hand, let us deal with same sum in a slightly different manner. Recall, the infinite sum we are dealing with is 1 plus minus half plus 1 by 3 plus minus 1 by 4, etc. Suppose we rearrange the terms of given series as follows. Minus 1 by 2, minus 1 by 4, minus 1 by 6, minus 1 by 8, plus 1, minus 1 by 10, minus 1 by 12, minus 1 by 14, minus 1 by 16, minus 1 by 18, plus 1 by 3, and so on. Note that here, before each positive term of the given series, we supply a block of sufficiently many negative terms of the given series. Now, let us find the sum of the numbers in these parentheses one at a time. Then it should be clear that the sum of given series can never be positive. So, what we observe in this example is ordering of terms appearing in an infinite sum matters a lot. With respect to a particular ordering, the infinite sum may amount to one real number, and with respect to another ordering, the same infinite sum may amount to a different real number. This is in contrast to finite case, where sum of finitely many real values will be always same irrespective of the order in which we added it. To sum up, in contrast to sum of finitely many real values, when dealing with sum of infinitely many real values, the question of whether ultimately it represents a finite real number or an infinite real number is not very clear. Secondly, the order in which we add infinite number of real numbers matters a lot. Thus, with this example, one should understand that when dealing with infinite number of real numbers and its summation, one should always first order the real numbers appearing in that summation. In other words, order is important. Well, a particular ordering corresponds to a sequence. Thus, while dealing with sum of infinite number of real numbers, one should not just start with a set of infinite number of real numbers, but one should actually start with a sequence of real numbers. Once you start with a sequence, a particular ordering is a priori given. Keeping all these examples and remarks in mind, we are going to make some formal definitions. To start with, let us fix some notation. Suppose that we are supplied with finite number of real numbers. Let us say a1, a2, etc. an. And we would like to deal with the sum a1 plus a2 plus etc. plus an. This finite sum, which can be always found by normal addition and which always amounts to a finite value, can be represented in a compact fashion using sigma notation. That is, by using uppercase Greek letter sigma, we denote a1 plus a2 plus etc. plus an in more compact fashion as follows: sigma ai I equal to 1 to n. Instead of writing the expanded form a1 plus a2 plus etc. plus an, we can represent it using summation or sigma ai I equal to 1 to n. This variable I is called index of summation. Note that the index of summation is dummy in the following sense. The sum a1 plus a2 plus etc. plus an can be written in compact fashion using the sigma notation ai I equal to 1 to n, or using the sigma notation as summation aj j equal to 1 to n, or as summation ar r equal to 1 to n. The value of the index which indicates the first term in that summation. Here I equal to 1, that is called lower limit, and value of the index which represents the final term in that sum is called upper limit. In this sigma notation, 1 is the lower limit and n is the upper limit. Slightly more generally, if we are supplied with a sequence AR, R equal to 1 to infinity. In a more explicit form, the sequence A1, A2, A3, A4 and so on is given to you. Suppose that we want to find sum of the terms AM, AM plus 1 and so on AN. We want to sum these terms. That is, we want to find AM plus 1 plus etc. plus AN. In fact, we are dealing with finite number of real numbers. So, by normal addition we can find this. This sum can be represented in a compact fashion as summation AI I equal to m to n. The lower limit should correspond to the first term in that sum and the upper limit should correspond to the last term in that sum. This is just to fix a notation which will facilitate to save time and space. Let us illustrate with example this notation. Find summation j square j equal to 1 to 5. Recall that this is a summation expressed in a compact fashion using Greek letter sigma, and what this stands for is 1 square plus 2 square plus 3 square plus 4 square plus 5 square. Do you see it? 1 is the lower limit, 5 is the upper limit, index is j, and you are finding sum of j square, j is from 1 to 5. And this is 1 plus 4 plus 9 plus 16 plus 25, which is 55. Again, to fix this notation in your mind, let us proceed with one more example. Find summation minus 1 power r, r equal to 1 to 8. Remember, this notation is used for a sum of finite number of real numbers. In this example, index is r, lower limit is 1, upper limit is 8, and this summation is used to denote minus 1 power 1, that is the first term, which is minus 1, plus minus 1 power 2, which is 1, plus minus 1 power 3, which is minus 1, plus minus 1 power 4, which is 1, and so on. Upper limit is 8, lower limit is 1. So, you are dealing with 8 terms. The last term is minus 1 power 8, which is 1. Since we are dealing with finite number of real numbers, this sum can be found in any order whichever is convenient for us. So, let us group in this manner. Finally, we get 0. Now, let us proceed with a definition. This definition is motivated by the examples that we have seen already and the remarks that we made. One thing is that while dealing with sum of infinitely many real numbers, there should be an order in which we add the real numbers. That is, we should start with a sequence rather than just an infinite set. Secondly, we cannot keep on adding and see what comes out when we are dealing with an infinite sum. Keeping all this in mind, let us make some definitions. Given a sequence an, the expression a1 plus a2 plus a3 plus etc. is called a series associated with the sequence an. Here is the definition for a series. Recall, we told sequence and series are interchangeably used in day-to-day life. Both of them mean successive events or objects, whereas in mathematics, sequence is used for ordered list. We did not see what a series stands for. Here is the definition. Given a sequence an, you consider the expression a1 plus a2 plus a3 plus etc. This expression is what we mean by a series. Thus, informally, the distinction between sequence and series is that sequence is ordered list of numbers, whereas series is a sum. Lot of questions remains here. Since we may deal with an infinite sum, it's not clear whether this expression has a meaning or not, in the sense whether this sum will ultimately give a finite value or not. Those questions can be answered later, but for the moment I would like you to understand the definition of a series. Given a sequence, the sum of its terms is what we refer to as a series. We will proceed with concept of series in next few classes. Thank you so much.